Hey, what's going on? All right, 2.3. So we're kind of going out of order just because it's what's working best with the block schedules. Probably already said that though on 2.4. Still summertime, so I'm not sure what we talked about yesterday because it hasn't happened yet. Okay, today is going to be a lot of writing, and I apologize for that. So I actually timed myself, you'll see in the corner, how long it took me to write all of this down so that I have an idea of how long you guys are going to need for this video. So I'm going to scroll through these pages for you. Sorry, I'm bouncing my table around. I'm going to scroll through these pages for you to copy down. So every time I move the paper, just pause me, and then I'll go back to the beginning. So I guess you're only going to be able to get those first two lines, and then I'll bump it up to the graphs. So go ahead and copy that top stuff above the line. Pause me. Okay. And then hopefully you can get much of this. Maybe just accept the little graphs at the bottom. So pause me. Okay. And then all this is just some blank graphs. So pause me again. Oh wait, sorry, you might have noticed I started writing something here. We're going to fill that in together. Yes, and we're going to do that several times. So, okay, pause me. Okay, page 2. So here's an example. We're going to need space here because we're going to write. So make sure you leave space there. And again, there's a blank we're going to fill in. There's a couple more, or maybe just one more down here. So go ahead and copy that stuff down and pause me. Okay, and there's the last of it. So again, we're going to fill in this example together, but just go ahead and copy all of this down. Pause me. All right, back to the beginning. All right, even and odd functions. You've learned about this before. So this is review. Much of first, I've probably said this several times, but much of first semester is review. So let me see which color I feel like working with today. I think I just heard my gate open. Interesting. Another joy of working from home. I'm sure that's going to happen a lot this year. All right, so remember that f of x just represents y. F of x is a placeholder for y. It means the exact same thing. The advantage of writing it using f of x is then I am telling you this thing is a function. You don't have to figure it out yourself, okay? So what I'm doing when I'm in this first if-then statement, I'm starting with a regular x and I'm replacing it with negative x. So think about it this way. I have, let's say I have a point, and I'm going to call it just regular old xy, thinking of positive values. If I then change this to a negative, isn't that gonna, the y is gonna stay the same, so I'm still gonna be lined up with this y value. The x is gonna be the same distance from the origin, just on the other side, so my point goes here, right? So what did I just do to that point right there? Maybe I'll ask you a question here. Maybe I won't, I'm not sure. We'll see what I decide on. Okay, so I'm reflecting that about the y-axis. Okay, this is a little bit OCD of me. So replacing the x with negative x is another way of saying reflect about the y-axis. And the way that I remember which one is which, we'll see what this one is in a minute, but these are two different things. The way that I remember which one is which is I start even function. I know an even function. So then I think about, I'm going to start a new graph. I don't want to draw on that graph and make it messy. I think about a really simple function that has an even exponent. So the easiest one I can think of is y equals x squared. So if I'm being asked about an even function, I think even, that leads me to even here. And I think about that graph. And what do I know about that graph? It has y-axis symmetry. So that's how, in my mind, I go from even function to y-axis symmetry. That's how I keep track of that, okay? You might want to listen to that one more time. All right. This one, I am replacing, this is the y value, right? And I'm putting a negative in front of y. And I'm also putting a negative in front of x. And let's figure out what that does to the graph. So just like we did before, I'll even line it up here, but I'm going to have to draw it like this, and you'll see why in a second. If I have an xy, just like I did before, thinking of them both as positive. Now, if I put a negative in front of the y, because remember, f of x is the same as y. If I put a negative in front of the y, that's going to go right here. Same distance from the origin, but negative instead of positive. And I'm putting a negative in front of the x, so that's going to go right here, same distance from the origin except negative positive. So now my point is there. That's my new point with this dynamic going on right there. That's called origin symmetry. So this is flipping along the origin. And an easy way to think of that is if I take this point right here, okay, you don't move your paper, just watch me. If I take this point right here and I rotate, I'm sorry, the graph. I haven't changed the graph at all, right? I had a point in the first and third quadrants in my normal sided graph, and when I rotated it, I had a point in the first and third quadrants. That's called, that's not called anything. I just rotated 180 degrees. So origin symmetry shows by a rotation of 180 degrees. Let me show you a little bit more without points. It's a little, I think it's easier to see. So let me walk you through my brain process. My brain process might not work for you, and that's totally fine. You just come up with your own. So if I'm being asked about an odd function, that's the first thing that's happening, right? Question is asking me about an odd function. I think about a very simple function that has an odd exponent. So my mind goes to an odd exponent. And then I got to remember this graph, which hopefully you do because it's been a while that we've been studying it. Y equals x to the third looks something like that. And then I think, well, what kind of symmetry does that have? Well, watch. I have the curve in the first and third quadrants. If I rotate my paper, I have exactly the same graph. That is origin symmetry. A rotation of 180 degrees gives me the exact same graph. So this is called origin symmetry. Another way of remembering that might work for some of you differently, OO, odd origin. Maybe that helps. And then if you can remember OO, then you just have to remember that even is y-axis symmetry. There is no x-axis symmetry because if I had x-axis symmetry, I wouldn't have a function. Let me take this away for a second. A sideways parabola has x-axis symmetry, right? Let's hypothetically, this is the x-axis. Doesn't pass the vertical line test. So these can't be called, something with x-axis symmetry can't be called a function, odd function or even function. All right, so quickly take a minute, pause me, and determine whether the graphs are even, odd, or neither. Okay, so hopefully here you got, this one has y-axis symmetry, which means that it is even. So going reverse from here, I could say y-axis symmetry. Okay, what graph has y-axis symmetry? So in my brain, I think y equals x squared, and then I think, okay, x squared, that's a 2, which is even. So that's how I go in my head from y-axis symmetry to even, the opposite direction of what I explained above. All right, this one does not have y-axis symmetry. If I fold it over that y-axis, they will not overlap. And then look here, I've got touching the positive x-axis and then going up in the first quadrant. Let me see if I spin it. No touching in the first quadrant. So this has none, neither. Okay, and then this one, please know my graphs are not going to be perfect. You're going to have perfect graphs in your homework and on quizzes and tests because they'll be computer generated, but just hopefully you get the gist of what I'm trying to draw here. So I don't have y-axis symmetry. If I flip this portion of the graph, it's going to end up in the second quadrant. It is not symmetric. However, I have this little lumpy thing in the first quadrant and then another little lumpy thing in the third quadrant. If I rotate my paper, first and third quadrants, so that means I have odd symmetry. I mean, an odd function, excuse me. Origin symmetry means the function itself is odd. Okay? All right, so these definitions probably freaked you out, but they're actually pretty straightforward. I promise you, you actually already know them. All this is saying, let me see if I can, there we go. All this is saying is, I'm going to use a brighter color to draw on these graphs. So x1 is less than x2. Let's start with that. x1 is less than x2. So these are subscripts, the 1 and 2. The proper way of saying these would be x sub 1 and x sub 2. It's just distinguishing two different x values. So the first one is smaller than the second one, which makes sense. They go in order. The first y value is smaller than the second y value. So for this ordered pair right here, the y value has to be smaller than this ordered pair right here. And that means the function that connects them is increasing. You can draw you can draw that in a lot of different ways. But that means the function that connects them is increasing. Okay, and hello, if the y value is smaller than the other y value, then of course it's increasing, excuse me. A function f is decreasing on an interval. So it's just talking about a portion of the graph, not the entire graph. Sometimes there are some graphs that are always increasing or always decreasing. It's just not very common. We're going to talk about a specific graph in a minute. So I want you to see if you can fill this in. Using this as a model, I want you to pause me and see if you can fill in what would go right here. Okay, so the more common way to say it, oops, I mixed that up. I was just copying above. So generally, we're going to keep the x1 smaller than the x2. That would mean then if we're decreasing, this guy needs to be larger than this guy. You might have switched this inequality around and left this one the same. That's fine. It's just not mathematical convention. So again, we have x1 and x2 in order. Now this is saying the y value for x1 is larger than the y value for x2. So x1 comma f of x1, that's 1 point. And x2 comma f of x2, that's another point. And if I connect those dots, of course, I have a decreasing function. Okay? All right. Ooh, sorry guys, this is a long one on a Monday. Wait, I don't even know if this is going to be a Monday, actually. This could end up being a Wednesday, for all I know. I mean, we don't know the schedule yet. That's where we're at in the summertime. All right, let me go here. Oh, we got to look at that figure in my book. Okay, figure 21 on page 83. Hopefully you're with me with your book, although I don't know if you have a book yet, so I guess I'm going to have to show it to you now that I think about it. Figure 21, and move my iced coffee so I don't spill it. Okay, let's see if I can do we need to zoom in a little? Okay. Determine where the function is increasing, decreasing, or constant. So increasing means going up from left to right. So I want to look for like a low point and see where it starts going up until it doesn't go up anymore. So everywhere from x equals -4 up to x equals 0. So this ordered pair has x equals -4. This ordered pair has x equals 0, right? The graph is going up from left to right. So I'm going to use interval notation to show that it's increasing from -4 to 0. Now, there's a calculus definition, which we may or may not have time to talk about at the end of the year. It's actually in the definition that we wrote on the previous page. Open interval. Open interval means does not include the endpoints. We can talk more about that when we get to calculus. Decreasing, so I want to know where it's going down. So it's going down from x equals -6 to x equals -4. Also, together with union from x equals 3 to x equals 6. So notice that these are x values. We're talking about where. When we use the word where, that's always going to be an x value. And then it's constant, meaning it's not increasing or decreasing between x equals 0 and x equals 3. Okay? All right, so let me move this out of the way. And zoom out a little. All right, so let's talk about these big scary definitions that aren't actually big scary. It's my job to make them not big scary, right? All right, so local maximum. Hopefully you noticed as you were writing these down, there's local and absolute. What does it mean if I say, I'm staying local this weekend? It means I'm not going very far, right? So that's what it means in terms of the definition as well. Don't worry about this whole open interval I containing blah, blah, blah. It's like, that's really scary. Yeah, those words. So a local maximum occurs when whatever the value is that we're talking about is greater than or equal to all the other y values. Whatever the y value is that we're talking about is greater than or equal to all the other y values. So in other words, it's the highest point in a small region on the graph. Okay? So see if you can fill in this blank for me real fast. Okay, f of c is less than or equal to. So this is the lowest point on some region of the graph. Okay, and I'll explain what I mean by some region of the graph when we actually look at a graph. If there's a number where it's the highest point for all of x values on the entire graph, that's where it's an absolute. So local is I'm looking at just a portion of the graph. Absolute is I'm looking at the entire graph. Notice again, we're talking about a location here. It occurs where? Yeah, that's an x value. The y value is the maximum or minimum itself. And then this one, see if you can fill in that blank real fast. Pause me. Okay, so it's going to be an absolute minimum if it's the lowest point on the entire graph. That's basically what that says. I hope that you paused me and wrote down all those things. So much writing today. I understand. You will learn about me that I really hate words. I will say that so many times. I like to be as concise as possible and use as few words as possible to get my point across. But sometimes there are just so many definitions that we don't have a choice. And this is one of them. All right, at which values of x? So I really want you to pay attention to whether the question is asking for an x or a y. This is asking for a location, which is always going to refer to an x value. So a local min, remember it is the smallest point on a region of the graph. Smallest. It is the lowest point on a region of the graph. Oh, I was supposed to give you ordered pairs here. I apologize. So this point, these are all given in the problem. Okay, I'm not just making these up. This would be like on the graph in the book that you're looking at. So if I look at like a small region of the graph, like in here maybe, this point right here is a local min. At which x value does it occur? X equals -1. There's another region of the graph right here where this is also a local min. It is the smallest point, the lowest, I keep saying smallest, the lowest point. At which x value does that occur? X equals 3. And then there's another point in here where I look at a small region of the graph where that is the highest point. So that is called a local max, and it occurs when x equals 1. Okay, What are the local max and min values? The word what is indicating that they want a y value, not a location, but what the actual max and min values are. So we're going to say local max. So for x equals, local max was right here. The y value is 2. And local min, we had 2 of them. We had a y value of 1 and we had a y value of 0. Okay. What are the absolute max and min values? So let's start with absolute min. Absolute min, let me leave some space for myself there. Is there a point that is lower than every single point on the graph? Yes, good. What is that point? It's 3, 0. Hold on a second. I just had to make note of the time really fast. Okay. We're talking about absolute min. And it's saying what? So it's asking for a y. It's not asking for a location. It's not saying where or at which. It's saying what. So that's asking for a y value. So the absolute min value is 0. Now here's a trick question. It's not really a trick question. Is there a point that is the highest point on the graph? Good. No. There are no absolute max is. That was weird. Okay. So that's it. We're done. Oh my gosh. Sorry. Those notes are so long. I promise you they're not always going to be this long. Sometimes they're going to be insanely short to make up for these ones that are longer than I want them to be.